Great. Hello, everyone. It's my pleasure to introduce Tyler Anway from University of Texas at Arlington, who will tell us about the classification of totally acyclic complexes over local Gorenstein rings. Tyler.
I had to figure out how to mute. Awesome. Thank you so much for inviting me to speak. And thank you to the organizers for putting this all together. It's a great opportunity. Also, thank everybody for showing up to listen to me talk for an hour. Hopefully, hopefully what I say is interesting. So yeah, today I'm going to talk about a classification scheme for rings of a certain type. Let's start by setting the stage and discussing some preliminaries. So let's start by, hold on 1 second. So we're going to start by letting R and K be a commutative local ring. And then over such a ring, we say that a complex C, so we'll write out this complex here. So we say that a complex is totally acyclic if it satisfies two conditions. So the first being that each of these CIs, so each CI is a finitely generated surjective R module. And if the homology at each degree is trivial, and the homology of the dual is trivial. And this is for all n. So what I mean by this is we have an acyclic complex in one direction, or we have an acyclic complex, and then when you dualize it, it is also acyclic. A little bit more, if you take the collection of all totally acyclic complexes, right? And just for future reference, I often denote or abbreviate totally acyclic complexes as TAC. So if you take all totally acyclic complexes together with the homotopy classes of morphisms, what you get is the category Ktac R. Right, and there are, I mean, this is a really nice category. It's triangulated. It's a thick subcategory of the homotopy category. Lots of nice properties to it. But there are also a couple of facts that I want to make apparent. Over a Gorenstein ring, there is a formal process by which we can associate an R module to a totally acyclic complex. Let me say this. And this is via a complete resolution, right? It's not terribly important that we know what a complete resolution is. Just know that there's this formal process linking a module and a totally acyclic complex. I also want to mention that in Ktac, every complex is homotopic equivalent to its minimal complex, right? And a homotopically equivalent is kind of like isomorphism in this category. So, you know, any complex we're discussing, you can take it to be minimal, which is nice. So the goal of this talk is we want to develop a classification of totally acyclic complexes over certain rings. Right, and I'll make specific what those certain rings are. Now, in order to facilitate this classification scheme, I would like to, or we first need to define what an approximation is. And before we do that, I also want to kind of build this pair of adjoint functors so that approximations exist. So this pair of adjoint functors was first defined by Berg, Jorgensen, and Moore in their 2019 paper, Totally Acyclic Approximations, kind of on the nose. And this is actually where a lot of the work that I've done derives from, is this paper. Yeah, so before we get to the actual definitions of these functors, let's make a few assumptions about our ring. So we're gonna let Q be a Gorenstein local ring and assume there exists this ring homomorphism from Q to a ring R that is surjective, such that the projective dimension over Q of R is finite. So what this is going to do is this is going to allow us to view R as a Q module. And in doing so, we can actually use this to define these functors. So let's first take the Ascension Functor, specifically the one that takes elements of Ktac R to Ktac Q. So we say this functor T from Ktac R operates in the following way. We're going to take a complex here and map it over to TC, where TC is the totally acyclic complex built by viewing the image of the zeroth differential of the complex C as a Q module, right? So in other words, take your complex, kind of restrict your view down to the image of the zeroth differential, view that as a Q module, and then use that formal process that I was talking about earlier, this complete resolution, to get your totally acyclic complex. You know, as expected, this functor also operates on modules perfectly fine, morphisms perfectly fine, but it's not as important for this talk, so I won't discuss it. Of course, this would happen. Okay, so this is just going to stay here until I reset this. So what I'm going to do is I'm going to exit out and then restart. I apologize. Yeah, I'm good to go. Okay, so yeah, the Ascension Functor is built from, I guess, viewing M.C as a Q module. Yeah, so this functor works on morphisms, of complexes is perfectly fine, but it's just not as important for this talk, so I won't go into it. The descension functor is actually much more simple to define. It is simply the change of rings functor. So we'll say S from Ktac Q to Ktac R takes a complex C to SC, which is just C tensor over Q with R. And similarly, it takes morphisms to the homotopy equivalence class of F tensor. Right. So Berg, Jorgensen, and Moore in the very same paper prove that these form adjoint pair. Right? And this will become apparent why this is important later on. So once we have this definition of an approximation, once we have these two functors, I'd like to now define what an approximation is. And it's a little bit wordy, but we'll break it down. So these were first defined by Auslander and Smollow in 1980, and independently in 81 by Enox. And what it says is if you take a full subcategory chi of a category, a right chi approximation of an object C is a morphism, and this is important, it's the morphism from X to C, where X is in chi and it is kind of minimal, right? So what I mean is we have this map here, which takes an object in whatever subcategory you're focusing on and maps it into the object that you want to approximate. And it does so such that if you have any other map, it must factor through our approximation, and therefore it's kind of minimal in some sense. I want to note that oftentimes I will say that this X, right, this object is the approximation, but if we're speaking totally formally, the morphism here is actually the approximation. So just so there's no confusion. All right, well, great. That's the definition of an approximation. How does this help us? Why did we just define this? Well, so two things. Since S and T are adjoint, there exists a co-unit map, right, which takes, we'll call it epsilon, which takes ST to the identity functor, right? And therefore, for any complex, right, we get the induced map epsilon sub C, which takes STC to C. And it is this map exactly that satisfies this above property here. All right, so in fact, in Ktac, we do have the existence of approximations. Okay, so that's kind of how we get them, but why are they important? What do they allow us to do? And I think that this next example that I have written here should really illustrate how we can actually approximate by a much more simple complex. So if we take Q to be this polynomial ring in two variables modded out by x squared, and R to be the quotient ring of Q modded out by y squared, then the R complex, which is associated to the field, the residue field, is given by this complex here, which is notably of, it has linear growth of the Betti numbers. So its complexity 2. right? But when you take its approximation over this ring Q, you get this periodic complex. So it's complexity 1. And so by looking at its approximation, we are reducing the complexity, which is nice. Okay, so now that we have this notion of approximations and we know that they exist in Ktac, what I'd like to do now is actually define our classification scheme. In order to do this, we're going to assume further. So that our ring Q is Henselian. And it should become apparent why I'm making this assumption later on. But it's basically so this definition is well defined. All right, so let's dive in. So the first thing we're going to do is let lambda be the set of all distinct, indecomposable, totally acyclic complexes in the image of S. So already this is kind of meaty, but what I mean by that is by looking at this adjoint functor pair up here, if we take all the totally acyclic complexes here in Q and we map them down by S, right? And then we take that set and only look at the indecomposable ones. That's what I mean by this lambda, right? So once we have that set in mind, then for any complex in our category, we can write its approximation as the direct sum of powers of those indecomposable complexes, right? So if you just cycle through all of the indecomposable complexes in Ktac, or in the image of S, you can write your approximation as that direct sum with a trivial summand, just because they can kind of pop up, right? So in this summand, T is a contractible complex, and all but finitely many of these powers must be 0, right? And that's because totally acyclic complexes have finitely generated projective modules, right? So we shouldn't be able to have infinitely many non-zero powers. Okay, so once we have this decomposition, we can say, we can finally make the definition of an Arnold-tuple as being the Arnold-tuple of C is just kind of this tuple of the powers of each one. Hopefully that makes sense. Are there any questions on how I'm defining what an Arnold-tuple is?
Could I ask a slightly different question? So
Sure.
for your functors, why do you need the projective dimension of R to be finite over Q? I think I missed it.
So I know this, but you know, being on the spot, I'm blanking. I know it has to do with making sure that this T is well defined.
I think it's the other way. I think you need it for S to be well defined.
Yes, yes, you're right. I think because if it's not, then when you just tensor down, you're not gonna, you won't necessarily get a totally acyclic complex. Is that right?
Okay, cool. Thanks.
Yeah, no problem. Okay, so we have this definition of an Arnold-tuple, and I want to state some facts about this definition. So if we take two complexes, C and C prime, in Ktac R, such that C is homotopically equivalent to C prime, then we must have that their Arnold-tuples are equal. And so this shows that Arnold-tuples are well defined up to homotopy, which is important because if two things are, isomorphic in this category, hopefully they should have the same, they should be in the same classification. It should be in the same class. Here's a note on some terminology. We say that C and C prime are what I'm going to call Arnold equivalent if they have Arnold tuples that are equal. Right? And so this is going to kind of form the classification scheme, right? So we say that they're in the same class if they're Arnold equivalent. One more fact about this definition here. So let's say that we have two complexes which are Arnold equivalent. This does not imply that C, or it's not necessary that C is homotopically equivalent to C prime, right? Which is good, because if that were the case, then why not just use homotopy, right? This next example actually should illustrate this quite nicely. So let's take Q to be this power series ring in two variables modded out by x squared, and R to be Q mod y squared. Then by taking C to be this complex of period 1, and C prime to be this complex, let me actually write this because this is important. This is period 1, and C prime to be this complex here with linear growth in the Betti numbers. If anybody's interested, I can give you the differentials or the, how to define this complex later on. But specifically, it has complexity 2, right? Because it has linear growth of the Betti numbers. Now, these are clearly not homotopic, as one is complexity 1, the other complexity 2. However, when you approximate each of these, you get the same exact complex. It's this periodic complex with degree 4 or rank 4 free modules, right? So, so indeed, Arnold equivalence is a more, I'm going to say, coarse description homotopy. Right. So now there are some drawbacks here. In general, this lambda set can be very large, right? And given one of these large lambda sets, I mean, the ordering on our Arnold tuples is a bit ambiguous. Right? So to help address these concerns, we're going to employ the age-old tradition in physics of assuming spherical cows. That is to say that we're going to make some assumptions to simplify our theory. This is where we introduce the finite CM type. So if we take Q to be a simple singularity, and by that, I mean, it is of this form here, where it's this polynomial ring where K is algebraically closed and of characteristic 0. And we mod out by a non-zero divisor F, having one of these following forms, right? We get a simple singularity. For a full accounting of this, we can look to Yoshino's book, CM modules over CM rings. But why this is important is that over simple singularities, so let me say this, over such a ring Q, there are only finitely many indecomposables, maximal Cohen-Macaulay modules, right? And these are called rings of finite Cohen-Macaulay type. So obviously these are important in their own right, and I believe they were fully classified back in the 80s. But the question becomes, why are they important to me? Why do I care about these rings of finite CM type? Well, there's a fact that given a totally acyclic complex, you know, here, we know that each syzygy, say, which is equal to the, is a maximal Cohen-Macaulay module, right? So if this, so for any totally acyclic complex, this is a maximal Cohen-Macaulay module.
Tyler, should the subscript on that differential be I+1?
Definitely should be.
Thank you.
I'm just so used to writing like 0.
I feel
Again,
you.
I write a 0. Yeah. Right. So each syzygy is a maximal Cohen-Macaulay module, and so we know that thus if there's only finitely many indecomposable maximal Cohen-Macaulay modules, then there's only finitely many indecomposable totally acyclic complexes over Q, right? And actually, I can do a little bit better than that. Let me say this specifically. We show that if M is an indecomposable maximal Cohen-Macaulay module, then there exists a totally an indecomposable totally acyclic complex C with the image of the 0th differential equaling M. And vice versa, meaning that if we take an indecomposable complex C and view its the image of the 0th differential, that is going to be an indecomposable maximal Cohen-Macaulay module as well. We actually go a little bit further, and so let me say this. In fact, for any such pair, so M and C, we have that the endomorphisms over M are isomorphic to the endomorphisms over C as rings. Right? Let me state one more fact. So over Q, so like under the assumptions that we have, the endomorphism ring of M is local if and only if M is indecomposable, right? And so using kind of all of the things that I've written so far, we can state that for any indecomposable totally acyclic complex C, we have that its endomorphism ring is local. Right, so why is this important? Why am I saying this? Well, all of this to say that Ktac Q is a Kroll-Schmidt category. Right? So why bring this up? What does this give us? Well, it gives us two important things. It gives us one, that there are unique decompositions, and two, that AR quivers can be defined, right? And it's the second one that I'm really going to kind of dive into here. I mean, the first one is important, but let's dive into this fact that AR quivers can be defined. So I should probably tell you
I wonder if it'll get fixed if you erase that sentence. I don't know.
I don't know that I actually even can. Oh gosh, what did I do? Again, I apologize for my technical issues. Yeah, so I should probably tell you a little bit about an AR quiver. Just briefly, an AR quiver is a directed graph, which is used to visualize underlying module structure. And the vertices of this graph. So the vertices are the indecomposable maximal Cohen-Macaulay modules. And the edges are what we call irreducible morphisms between the two maximal Cohen-Macaulay modules. It's not super important what irreducible means in this case, but I have showed that irreducible morphisms over maximal Cohen-Macaulay modules can be lifted to irreducible morphisms in Ktac. And I mean, in fact, much of the work that I've done so far has been to take these ideas and concepts of AR quivers over finite Cohen-Macaulay type rings and actually lift them to the case of the triangulated category Ktac. So what I'd like to do now is kind of give an example of one such extension. So if we take Q to be this power series ring in two variables and mod out by x squared plus y to the fourth, this matches up with the simple singularity type A3. So when you write out the AR quiver, it looks something like this, where you have Q into this module here, defined by the co-kernel of this 2x2 matrix. And it splits into n minus and n plus, where these are given by the co-kernel of x plus iy squared and x minus iy squared, kind of opposite respectively. You might notice that these are actually matrix factorizations of this of the polynomial we're modding out by. That's kind of how these are defined. But so this extension, or this AR quiver here, has an extension into totally acyclic complexes as follows, right? So this M1 extends to E1, N minus extends to E minus, and N plus extends to E plus, where these are given by these totally acyclic complexes here. So you'll note that here we have this periodic complex where the syzygies are actually this M1, and E plus has kind of opposite syzygy X minus IY, or X plus IY and X minus IY. And something interesting to note about these two is that E plus is actually just a shift of this E minus complex and vice versa, right? The other question you might ask is, well, what happened to this Q here? Well, because Q has finite projective dimension over itself, right, then the associated totally acyclic complex is just the trivial complex, right? So this kind of extends to the zero complex. Right. So yeah, this is one example of how you might extend to the category Ktac. And I've actually done this type of extension for all of these kind of A's, D's, and E's, but they can get quite complicated. Apparently my Microsoft Outlook is verifying. So yeah, let's turn now back to these Arnold-tuples and discuss what they mean over finite Ktac type rings, right? Finite Ktac type, just finitely many totally acyclic complexes. So if Q is a simple singularity and R is Q modded out by some regular sequence, then that lambda set we had is finite, right? And in particular, for Q equal to this A3, that lambda set was the set consisting of three objects, S of E1, S of E plus, and S of E minus, right? So you just take the three elements in the quiver and you map them all down to Ktac R by S, and there's your set lambda, right? So this is really nice because when we were defining Arnold-tuples, right, you're kind of seeing what building blocks go into the approximation, right? Well, over a ring of finite Ktac type or finite Cohen-Macaulay type, there are only finitely many of these building blocks, so it simplifies our theory a lot. I would like to kind of give this last example here where we look at one such approximation over the ring that we were discussing here, A3. Okay, let me take a sip of water. So if we let Q be A3, and we look at R being the Q modded out by X squared, then for C and Ktac R, given by this complex here, where the kind of, it's built from the image of the zeroth differential being this co-kernel, when you approximate it, you end up with this periodic complex where you have rank 5 free modules, and the differentials are given by these two matrices here. One thing that I'd like to point out is that if you look here and here, right, these are the, these are I mean, basically it's just, it's this complex here, right? And so you can see that we have not only one, but two direct sums of the E1, right? And then, but we have this kind of trivial piece down here where it's just going to alternate back and forth between 1, 0, 1, and 0, right? So we can actually say that STC is kind of equal to S of E1 direct sum, it's not a direct sum, E1 direct sum, some trivial piece, right? And so we would say that the Arnold tuple for this complex is actually just 2, 0, 0. Right. Right. Well, so I'd just like to kind of briefly talk about some of the directions that I'd like to take this in the future. And there are three main ideas that we have. So we know that if you have a trivial Arnold tuple, meaning that every entry in your tuple is 0, this happens if the projective dimension over Q of the image of your zeroth differential is finite. And so what can we say, you know, what properties correspond to these trivial Arnold tuples? Right. Another direction is what properties are shared if C is Arnold equivalent to C prime. And along that same kind of train of thought, what can be said if the Arnold tuples are disjoint, right? And so what I mean by disjoint is that they share no common building blocks in their approximation. And so, I mean, if that's the case, then they must be like fundamentally different in some way. And so we're curious as to, you know, what we might be able to say in that case as well. But yeah, that's all I have for today. I think I ended a little bit early, but yeah, if there's any questions, I'd love to hear.
Let's thank Tyler. And any questions? So I have one. The S and T, I mean, the composition even depends on the choice of Q. And I'm thinking about this general setting that you've got where R is isomorphic to Q mod some ideal of finite projective dimension.
Mm-hmm.
And just wonder what makes a good choice there, right? Because you had this example where I think Q was when you mod out by x squared and then you mod out by y squared in order to get down to R.
Talk about is it this one you're talking about here?
Yeah. And so you chose Q to be that hypersurface, but you could just as easily have chosen Q to be the power series ring itself, in which case T would be very trivial and ST would be very trivial, right?
Yeah.
So can you give any idea of what makes for a good choice of Q?
Yeah, so I mean, we have that all totally acyclic complexes over what is it, something of codimension 1 are periodic, right? And so, I mean, that would make a good choice because now you can take, I mean, you can mod out by, you know, take Q to be something as codimension 1, and then let your R be, you know, any length of regular sequence. And then now you can take something with, you know, a huge codimension and approximate it by these complexes that, you know, are necessarily periodic of period at most 2. So that's really nice. You know, also by take Q to be one of these rings of finite CM type, now we're looking at you know, something with only finitely many building blocks. So there are only finitely many kind of distinct choices to take is what you can approximate. And so, you know, if we kind of look at how these building blocks affect the building blocks of the approximations, kind of what that can tell us about our original complex, then now we only have to kind of look at finitely many of them and see what you can get from that. Does that answer your question at all?
Somewhat, yes, thank you.
Somewhat.
Any other questions for Tyler? I do like this question that Josh asked about finite projective dimension. It was the first thing that I thought of, and was wondering, so you need some restrictions, but be curious to know if you could get something similar if you just have finite complete intersection dimension. Right.
Yeah.
Those tend to respect a lot of things. It's not clear whether it respects enough.
That's certainly something I can look into. I mean, anything to, I know I make a lot of assumptions throughout this. So anything to kind of cut back on those assumptions would be nice. Yeah, it's certainly something to look into.
Last call for questions. All right, let's thank Tyler again.